Hi, my name is Hannah Kasevsky, and I'm a PhD student from Professor Ilana Nisky's lab in Ben Gurion University in Israel. And today I'm going to show you some of the work we've been doing that leads us to believe that tactile and kinesthetic information might not be integrated according to maximum likelihood in stiffness perception. So first, a quick introduction. The information we receive through the sense of touch is comprised of two modalities. There's the kinesthetic information, which is sensed in our muscles, for example, forces that are applied on us, and tactile information, which is sensed by mechanoreceptors in our skin. For example, stretching of the skin of our finger pads. And we combine both types of information to form our perception. For example, our perception of stiffness, which is how stiff an object feels to us. So previous studies have shown that stretching the skin of the finger pads more than it would be during a natural interaction causes an object to feel stiffer than it really is, meaning it increases the perceived stiffness. And the question we are trying to answer here is, how are the tactile and kinesthetic information integrated in stiffness perception? And specifically, are they integrated according to maximum likelihood? If this were to be the case, it would mean that the total perceived stiffness would be a weighted combination of the information received from the two modalities. According to maximum likelihood, introducing uncertainty into the information received from one of the modalities would lower the weight the nervous system would attribute to this information. In order to answer the question of, are the tactile and kinesthetic information integrated according to maximum likelihood, our first step was to try and find a way to introduce uncertainty into the information received from each of the modalities, and to then examine how it affects the weighting between them and see if it corresponds to a maximum likelihood. So to do this, we designed an experiment that was comprised of trials, and in each trial, participants probed two different virtual objects and decided which of the two felt stiffer to them. Participants probed the virtual objects using an experimental setup shown in this image by making downward probing movements. And when they did so, force was applied proportionally upward, creating kinesthetic feedback. And a tactile skin stretch was created using these red tactors that moved against the finger pad skin. In our first experiment, the method we used to try to introduce uncertainty was adding noise to the tactile signal, but we found that this method did not create uncertainty. Therefore, in our second experiment, instead of trying to create uncertainty by adding noise throughout each of the probing movements into the virtual object, what we did was to define upfront how many times participants would probe each of the virtual objects and varied the amount of skin stretch applied by a given object between consecutive interactions. And we hypothesized that doing this might create uncertainty regarding the tactile information. We did the same thing to create uncertainty in the kinesthetic information, but just by varying the stiffness level of the object between the consecutive probing movements. This experiment had 4 experimental conditions. So the yellow bar represents trials in which there was force and no skin stretch, green, force with skin stretch, pink, with skin stretch and variability in the stiffness level, and blue, skin stretch and variability in the amount of stretch. The y-axis shows the average effect of each of these conditions on a value called the JND, which indicates the amount of uncertainty experienced by the participants. So by comparing between the pink and green bars, we saw that introducing variability into the kinesthetic information led to more uncertainty than the skin stretch without the variability, meaning kinesthetic uncertainty was created. So we then looked at what maximum likelihood would predict in the event of kinesthetic uncertainty. And specifically, we looked at a value called the PSE, which indicates the perceived stiffness of the virtual object. So by comparing between the pink and the green, we saw that in this case, maximum likelihood predicts an even larger increase in the perceived stiffness due to the added kinesthetic variability. We then looked at the perceived stiffness found in our experiment to see if it corresponded to the maximum likelihood predictions. And what we saw was that in our experiment, the kinesthetic uncertainty did not lead to a larger increase in the perceived stiffness and may have even had the opposite effect, leading us to believe that tactile and kinesthetic information may not be integrated according to maximum likelihood in stiffness perception. So just to conclude, in our experiment, we created kinesthetic uncertainty, but it did not affect the weighting between the two modalities in accordance with maximum likelihood, leading us to believe that tactile and kinesthetic information may not be integrated according to maximum likelihood in stiffness perception.